In this series, we will talk about Boolean and non-destructive modeling in Blender. To make that concrete, we're going to build something using Claude and the Blender MCP integration, a steampunk clock escapement. A mechanical assembly of gears, levers, and ornate details, modeled mostly using Claude and the Blender MCP integration, with as minimal user interaction as possible. Everything you see here, the escape wheel, the anchor fork, the decorative backplate, the brass and copper materials, was built through natural language prompts to Claude. We describe what we want. Claude writes the geometry. Blender executes it in real time. If it does not look right, the geometry is built from simple 2D shapes that are easily editable. The series runs 7 segments. Each one picks up where the last left off. By the end, you'll have a complete non-destructive workflow you can apply to anything mechanical that follows this same process. This first segment is the orientation. We cover the mechanism, the tools, and the visual direction. Segment 2 is where we start building. Before we touch a vertex, let's understand what we're actually building. A clock escapement is the mechanism that controls the release of energy in a mechanical clock. It's the part that makes a clock tick. It has 2 main components. The escape wheel, a tooth ratchet gear that wants to spin freely, driven by the clock's mainspring or a hanging weight. The pallet fork, an anchor-shaped lever that catches the teeth one at a time, rocking back and forth to release them in a controlled rhythm. Each time the fork catches a tooth, the pendulum is given a small push. Each time it releases, the wheel advances by exactly 1 tooth. Every tick, every tock, that's the fork catching and releasing. The faces of the pallet jewels have to be positioned at very precise locking angles, or nothing works at all. That precision is actually what makes this a great modeling subject. The geometry is driven by function, and function means measurements. And measurements mean we can describe everything to Claude in numbers rather than freehand sculpting. Booleans get a bad reputation in Blender. People say they're slow, they're messy. They destroy topology, and they can if you apply them incorrectly. The approach in this series is non-destructive Booleans. The cutter object stays live in the scene. You can move it, scale it, reshape it at any point, and the cut updates automatically. Nothing is baked, nothing is permanent. Here's what that means in practice. Say we drill a bolt hole in the backplate, and 3 segments later, we decide it's in the wrong spot. In a destructive workflow, you're manually filling the old hole and recutting or rebuilding the whole shape again. In our workflow, you select the cutter, move it, resize it, or modify it, and you're done. The Boolean modifier recalculates, no redoing work. The modifier stack order matters. Boolean goes at index 0 below everything else. Above it goes the bevel modifier, then smooth by angle. That order means the Boolean cuts happen on the base geometry first, then bevel rounds the hard edges, then smooth takes care of shading. If you flip that order, the bevel runs on uncut geometry and nothing looks right. We'll follow one other rule throughout. Cutter depth is always target thickness plus 2 millimeters. That 2 millimeter overshoot prevents what Blender calls coincident faces. When the cutter surface exactly lines up with the target surface, the Boolean solver can't decide which side is inside. By the end of this series, that stack, Boolean, bevel, smooth, will feel like a reflex. We're using Claude and the Blender MCP integration throughout this series. If you followed along with any previous work here, this layout will look familiar. Claude is connected to Blender over a local TCP socket. The add-on is live in Blender. The terminal is open in PyCharm, and everything is ready to go. The setup process is covered extensively in other resources, so we're not going to walk through installation today. What you'll see in each segment is a feedback loop. Describe, build, review, redirect. We give Claude a natural language prompt. Claude writes Python against the Blender API. Blender executes it, and we look at the result. If something's off, a dimension is wrong, the origin is misplaced, the modifier stack order isn't right, we describe the correction, and Claude fixes it. Claude's first attempt isn't always correct. That's fine. The back and forth is part of the workflow, not a failure of it. Let's start the project. We'll ask Claude to set up the scene from scratch. The scale of the image doesn't look right, so I'm going to ask it to adjust that for us. Much better. Now we have a strong base to work with. And there's our starting point. I'm just going to go ahead and save the file here. So we have a clean scene millimeter units, 4 collections organized in the outliner, reference image placed and visible in the viewport. Before we start modeling, the visual direction. Steampunk means brass and copper, warm metallic tones with visible age and wear. It means exposed mechanical parts that look like they belong in a Victorian workshop. Slightly oversized proportions, decorative cutouts that serve no mechanical purpose but look like they should. The material palette on this project is 3 shaders. Brass for the escape wheel and main moving parts, that warm gold with slight roughness variation and edge wear. Copper for accent rings, collars, and secondary details. Reddish tint, tighter specular, and dark iron for the frame and backplate. Each component is assigned one of these 3. The escape wheel is brass. The pallet fork is brass. The arbor shafts and collars are copper. The backplate and frame are iron. The detail level is adaptive. If we're building fast and the timing is ahead of schedule, we add filigree cutouts and rivet arrays to the frame. If the mechanical geometry is taking longer, we dial back the surface decoration. The core escapement, wheel, fork, frame always ships. The ornamental layer is the flex budget. In the next segment, we block out the escape wheel, the tooth ratchet gear at the heart of the mechanism. We'll draw the asymmetric tooth profile as a flat face, solidify it to give it thickness, and use an array modifier with a pivot empty to rotate 30 copies around the center. The teeth will be discrete iterations of a simple 2D face, so changes are simple to implement. Thanks for watching, and that's all, folks.